All right, sorry for the technical glitch. Okay, so I'll just dive right into it because there's already been tons of great material about the CGM already. So this talk will fundamentally be about the radiative Kelvin-Helmholtz instability, and what's the saturated state of the radiative Kelvin-Helmholtz instability. And you might think that we should really know this by now. It was actually difficult to find studies of the saturated state. And the Kelvin-Helmholtz instability is something which is always used to validate numerical codes and is notoriously difficult to get right. There was a recent paper by Daniel Lacornier where they showed you just need crazy resolution with a standard Godunov code to achieve convergence. And you also always need to put something else in, right? So MHD is fundamentally scale-free. So you need viscosity, you need rate of cooling, you need something, thermal conduction, right, to impose a scale. And so the theme of this talk is that cooling will introduce that characteristic scale for you, radiative cooling. And I will talk about two applications. One is something we argued a lot about yesterday already, coal gas entrainment in winds. And another one is turbulent mixing layers, right? And whether it can produce the O6 we see, something that we talked about this morning. Okay, so all the work here was done by Max Gronke. So Max is an expert on radiative transfer, and he's going to be a Hubble Fellow at UCSB in the fall. And he got sick of running his radiative transfer code on other people's simulations, so he wanted to start making his own simulations. And so this is his first hydro stuff, and we may have bitten off a bit more than we can chew. But anyway, you'll see what we came up with. As already has been discussed over the past few days, we see lots of coal gas outflowing at high velocity, and how does this happen, right? There's an entrainment problem. The feedback mechanisms we talk about mostly affect the hot gas, but for the most part, we can only see the coal gas. That most of the gas we see is in quasar spectroscopy. And this is not easy. And the fundamental reason you can sort of write down very quickly. If you want to accelerate a blob of coal gas, you basically have to sweep up of order that coal gas column density in the hot gas, right? And you compare that with the destruction time, which is of order, the Kelvin-Helmholtz time, which is also of order the Rayleigh-Taylor time. And this is shorter by a square root of the density ratio, right? So before you can accelerate, you will destroy the cloud, right? And so there was a nice recent paper, Norm was an author, which sort of had a catchy headline, right? Entrainment in trouble. So, so we see it in nature. So how did it happen? This estimate is, assumes adiabatic physics, right? So you might think, well, radiative cooling should help, right? And a number of early papers pointed that out, including the pioneering paper of Klein et al., which was really the first. Well, it was a formative paper in the study of cloud crushing. But many recent detailed hydro simulations show that, well, it's not possible, right? So Evan talked about this yesterday, but they all show that cooling could potentially extend the lifetime of a cold cloud, but eventually it just Kelvin-Helmholtz mixes and gets destroyed. So if you don't mind, I'm going to replay the movie you showed yesterday because it's really nice illustration of the problem, right? And this is a billion grid cell simulation. So this is Evan simulation, and you see that you hit this thing with the wind, and you get a spray of cloudlets forming, and there's this. They tend to spread out, right? If you could look carefully, you would see that there's a bow shock forming, and they become more and more diffuse. These tiny cloudlets slowly mix away, and then you're done. So this is one of my favorite mottos. So our intention was not really to try and solve the the entrainment problem, right? So we wanted to start playing with just some things, and then we ended up with something that we really did not expect. So like 2 years ago, Mike McCourt had this, in my opinion, really nice idea, really simple, but I thought really cool idea, that actually there's a characteristic scale in cold gas. And the basic argument is very simple, right? So, you're familiar with gravitational instability, right? Where there's a characteristic scale, the Jeans scale, right? When the sound crossing time is of order the gravitational collapse time, the free fall time. And so that scale is essentially the sound speed times the free fall time. And if you have say a cooling instability, then what breaks things up are pressure gradients, right? So you could have a fragmentation instability where there's a characteristic scale, but this time you set the sound crossing time, which maintains pressure balance, to the cooling time, which tends to drive pressure gradients. And I've been trying to promote this thing as the McCourt scale. I've gotten no traction whatsoever. But anyway, I'm going to keep labeling that. It's just the sound crossing time times the cooling time. And this scale is very small because if you're in pressure balance, and I know Jeff said that often you're not, but if you are, then densities can be quite high for the pressures that we tend to see. And this gives you a very small scale, which is not resolved in most galaxy simulations. So this was something that we were excited about, and the thing that we were really excited about was that he did a study of a wind going past a cloud in 2D, mind you. So there's a 2D simulation, and at the end of the simulation box, the cold gas was co-moving with the hot gas. And we thought, well, maybe this is some kind of collective effect. You break up into small things, and you vastly increase your surface area to volume ratio, so it's easier to entrain. We weren't really sure what was going on, but we tested this, and we were confident this is what at least these 2D simulations were telling us. And we did one more thing. Mike did one more thing, which was to take a whole swarm of cloudlets and blow a wind past them. And you would see these large structures forming. And I don't want to go into the details of all of this, but what you would see at the end of the simulation was entrainment. So the hot gas and the cold gas velocity became very similar. And we thought that this was some complex phenomena, perhaps due to some collective effect, and there was some kind of streaming instability taking place. And I still think there's room for that. Right? I still think there's something very interesting going on, but I won't talk about that today. The main thing was that what Max wanted to do was to try and dig into this a little more. And before digging into this, just to run some more basic simulations just to get oriented, right? So we decided, all right, having this very high resolution in 3D multi-scale simulations would be nice, but it turns out we think it may not be necessary for you to achieve entrainment. So I'm going to go straight to the punchline first. And it's not going to be the order. So we were confused for a very long time. And I'm just going to give you what we ended up with at the end of our confusion. And we now think this is right. I have to admit, you never know what happens at higher resolution. And these are fairly low resolution simulations. I'm already asking in mercy and advance from 1%ers who have 100 million CPU hours to be kind to the unwashed masses. But anyway, what we ended up concluding was that mixing is not the enemy, that mixing is your friend. And that what mixing does is that it draws in the mass and the hot and the momentum of the hot gas, so that you end up with more cold gas, which is co-moving because the hot gas is already co-moving, right? So it's somewhat similar to what Evan talked about. You want to convert the hot gas to cold, but instead of what you're using the cold gas as a seed, right, to create warm gas which can cool. So what does this mean? What do you need for this to work? You need cooling to be efficient, right? And what do I mean by that? So you can show that if you have a Kelvin-Helmholtz instability, a radiative Kelvin-Helmholtz instability, right, that the characteristic temperature of the mixed gas is of order the geometric mean of the hot and cold gas temperatures. And in pressure balance, so is the density, is the geometric mean. And so you can calculate the cooling time of the mixed gas, and it's not that big. Okay, you actually you win a little because you are often at the peak of the cooling function in the mixed gas, right? If you have 10 to the 4 and 10 to the 6 K gas, you end up with 10 to the 5 K gas. And you lose a little because it's less dense. But it's not too. It's definitely a significantly shorter cooling time than the cooling time in the hot gas. And so, if your cooling time of your mixed gas is, the sign of this inequality is wrong. If the cooling time of the mixed gas is shorter than the Kelvin-Helmholtz time, that means that when you supply, mixed gas, it immediately cools, right? Then you won't destroy your cloud, but you'll add mass to your cloud. And so this requirement corresponds to actually a constraint on the size of the cloud, right? And you can just go through the numbers, and it's not that big. But the thing is that a lot of simulations actually, they actually are in the limit where the cooling time is comparable to the cloud crushing time, or even larger. And the other thing, when we were trying to interpret our results, we thought there could be very interesting physical effects, but it turns out that there was no really profound physical explanation for what we were seeing. One other thing you really need is you need a very long box, and you need to be in a frame where you move along with the cloud. And if you don't, because all of the mass growth is happening in the tail. So if you don't capture the tail, you miss out the mass growth. And there's an interesting effect which cooling does, which is a focusing effect. So I know this is kind of weird to foreshadow all the results, but I wanted to put it there before you drift off. So these are the two things. So this is a very low resolution case because others have done this in much higher resolution, but we get essentially the same result, right? So if the cooling time is longer than the cloud crushing time, basically, you get a reverse shock going into the cloud, and then the thing gets wider and wider, and it dies. But the interesting thing is if you have a short cooling time, then what happens is that actually stuff gets stripped off the sides of the clouds, and then it enters the tail, it mixes, and all the mass grows in the tail. And sometimes, it enters the tail, and it stays there and only starts growing later on, which is why you need the long box. And you can see that after 12 cloud crushing times, this box, this is Athena 3D, by the way. This is a 3D simulation. And it's not terribly high resolution. It's about 64 cells across the cloud. Is pretty much entrained, right? The relative shear is only 5% of the wind velocity, and the cloud has grown in mass by a factor of 2.5. So here's a movie, and this is the case where it doesn't work, right? So this thing just splits up, and Evans was much better. But we did a lot of tests against the literature, and we basically get the same result in terms of the mass evolution with time. So against most of the cases that I put in that slide over there. Okay, but if you have fast cooling, or equivalently, a somewhat larger cloud, then you can see this focusing effect. And stuff moves into the tail and mixes there. And this focusing, we think, is driven by cooling. So basically, cooling in the tail causes low pressure here, and that causes pressure gradients that cause these things to move in. And you can see this if you on a high resolution screen. Okay, so what happens in the end is that, to our surprise, the cold gas grows in mass. And this comes from hot gas cooling out. So right, you can see it happens faster, in cases where you have lower density contrast because the cloud crushing time is smaller. So this is very busy, but these things are basically color-coded in terms of the ratio of the cooling time at the mixed temperature to the cloud crushing time. And the borderline is sort of this yellowish color. And you can see, indeed, for the yellowish stuff, it sort of dips down and then it barely recovers. If you're way above it, then your growth seems to saturate. We think this is because you are basically just limited by your mixing time. And if you're way below it, then game over, you're dead. And you can see that here, the coal gas becomes entrained, right? So the shear grows quickly. And if you look at some of those plots, so this is in units of cloud crushing time, but on the right side, that's in units of the drag time. And you can see that the entrainment can actually happen on timescales shorter than the drag time, which shouldn't be happening, right? So really what is happening is that it's not that your growth in coal gas, the reduction in shear you see is not because you're accelerating coal gas, but because you have a bunch of hot gas that cooled out. Yeah. Yeah, okay, so entrainment is the wrong word. So I'm just using it because it's sort of the dart, it's the bullseye that everybody's going for. So, okay. So to get with the program of Mark's talk this morning, we're catalyzing precipitation. Okay. Yeah, without gravity. Okay, so and then we did a bunch of tests. We tried to change resolution. There was a time when we were very confused about the effect of boundary conditions. In the end, it doesn't matter so much. You can change the floor temperature. You can put in heating. You can change the cooling curve. And again, these are not super high resolution. But when we increase resolution, the coal gas mass grows faster because mixing happens more quickly. And certainly, if you are in this game, I come to you in all humility, please try this on your own and see if you agree with us, because it was kind of a shock to us to see this. So we think this is right, but and it's Athena. It's not some, it's a well-tested code. And just make your box long enough. Make sure you make your box really long. That was the main reason why we tested against the other things, and when we had the same box size as they did, we recovered the same mass history. Okay, so there's lots of interesting things to do. Obvious thing is to put in magnetic fields, right, which will change the topology of the gas. You'll have MHD forces. We can argue about whether conduction is important or not, but if it is, then certainly it will change things. and also change heating prescriptions, photoionization, less idealized geometry. And it would be interesting to return to this original thing that we were interested in. What happens if you had really super high resolution, right? And there are streaming instabilities that people study in protoplanetary disks involving dust, right? Where you see stuff aggregating, which also would be very interesting to study. And here's a teaser from a study by Suoqing Ji. And it's a bunch of cloudlets. You apply a wind, and then these cloudlets are just inertial particles. So we certainly can't run this in full hydro where we resolve the cloudlets themselves. So they're just inertial particles. But you definitely see structure happening. So this summer, we want to understand what's going on there. But right now, our thinking is that would be really nice to understand better, but may not be necessary. And that, basically this precipitation or condensation is a fairly robust phenomena. Okay, so in the last 5 minutes, I'll try to move along quickly and just describe to you what if we dig into the turbulent mixing layers themselves, right? So I told you that you mix and you produce this intermediate temperature gas, and that's where all the action happens. In these simulations, those layers are not resolved all that well. So what if you do try to resolve them? Okay, so you heard all about O6, it's important. And so this is a picture that Suoqing took himself. It's an imperfect but okay, so there are two things. One is, could they be the source of O6, right? Turbulent mixing layers. So you produce 10 to the 5K gas. That's kind of ideal temperature, right? You do an order of magnitude estimate from the Begelman and Fabian paper I mentioned, and it looks good, Then you don't need to have a cooling flow or something like that to produce this gas, and it can potentially, because you're going to have a range of temperatures, this could potentially explain some of the coincidence between low and high ions in velocity space that Jess talked about, and perhaps an observed correlation between column density and B parameter. But also, we really want to, we want to test this order of magnitude estimate and just these analytic models of mixing layers against simulations. So there actually have been detailed 2D simulations of mixing layers, but they've never confronted just simple theoretical models. So a bunch of simulations. The main thing is that these are in 3D. We have non-equilibrium ionization. So Suoqing wrote a new flash used the flash module for that. But he also hacked it to put in photonization, and we also put in B fields. And okay, so this is what it looks like. The main thing that you should see in this is that the column densities are about 2 orders of magnitude smaller than what that simple order of magnitude estimate tells you. So that's not good for the O6 story. And it turns out that even the simple hydro case is hard to understand. At least we've had trouble. If any of you have thought about these issues, I would love to have a chat with you. There are a bunch of expectations that you would have from a simple estimate. You would expect that column density should be independent of metallicity, essentially because the cooling time at the peak of the cooling curve goes inversely as metallicity. And you would also expect that, that there's some dependence on cooling time, right? But the dependence on cooling time is weak, right? So these are, if you change the cooling time by an order of magnitude, there's some change in the column density, but it's not very large. But if you change the metallicity, there's an order of magnitude change, okay? And it turns out that if you analyze the simulations, the characteristic velocity is certainly not the shear velocity. It's about an order of magnitude smaller at least, and it's a function of cooling. And it looks like cooling is extremely important in generating the turbulence. And one simple way of thinking about it is that what we see is that the total pressure, the sum of the thermal and turbulent pressure, is actually continuous across the mixing layer. And if you have more cooling, you decrease the thermal pressure, and you actually have higher turbulence. So what happens is that higher turbulence compensates for the shorter cooling time, and you have a mixing layer of actually not that different a size, even when you, say, decrease the cooling time by an order of magnitude. And the mixing layer is powered by both energy inflow and turbulent dissipation. Okay, there's lots of details that maybe only a mother would love, so I'm gonna skip them. The main thing is, okay, magnetic field does what you expect it to do, right? It gets amplified to close to equipartition and suppresses mixing. So it's looking very bad for this as an explanation for 06. But it's still a very interesting theory problem. Okay, so then just to advertise that we can do photoionization. So bottom line is that we think that coal gas could survive and grow, and it would certainly be great if others could see if they ever will see this. And so turbulent mixing is not a promising source of high ions, but there's lots of interesting things about the details of these mixing layers, which we think are interesting. Certainly, if you want to understand this better, this whole focusing effect, how that happens, you really have to understand this problem. Thanks. Okay. Okay.
First is essentially, it seems like what you found is an equivalent to the field, right? In other words, the energy transfer is not moving as specifically your object is big enough, then transport energy from
I mean, turbulent mixing is a diffusive heat transfer process.
So there's really there's things that more believable thinking about it that way.
Right. Right.
The question is, are you tracking non-polarization?
So in the layer ones,
Right. I know you're in the layer ones. You said so, but I don't think that was saying about talking about non-polarization.
no. So those are, but I don't think they're important because we fooled around with the cooling curve a lot, changing it to the form where you change the ionization levels by photoionization and so forth. It doesn't seem to be terribly sensitive to that.
I'm listening to sensitivity. You look and see how much polarization can be.
No, that's easy. So we want to do observational diagnostics of this stuff, all of that, but we're big to do this.
Thought a lot about turbulent mixing layers. I don't know if you read my 2016 paper, the whole thing.
Yeah, no, I know you and Matt, you don't like it. And Matt always says, this Peng, he always likes these turbulent mixing layers. So
it's because the column densities are too low by a couple orders of magnitude. But, I mean, to fix that, you could just say that each line of sight intersects like 100 turbulent mixing layers. There you go, you got it. Problem solved. But one of the things, instead of just straight column densities, you could look at is...
the thing is that if you can't believe these two things simultaneously, right? Because we're saying that it becomes entrained and then there's no turbulent mixing layers.
Right.
Sorry.
So, one of the things you could also look at, if you're going to order observables, because you're just doing straight column densities, is column density ratios. And one of the things that people often use to constrain these things are ratios of like N5 to O6, silicon 4 to O6, and for some temperature density that you have with your ionization equilibrium or non-equilibrium models, you would get a prediction of those ratios. Those ratios tend to be fairly constraining. Turbulent mixing layers, though, I always liked because they got the ratios right, where so few models don't. But they get the column densities drastically wrong by orders of magnitude. So, anyway.
You can either, I guess the squishing also along with smoothing. Yeah.
So I had a similar question, actually. I guess the way to phrase it is, so how much O6 can you produce in a single mixing layer? Because the observations are showing like 10 to the 14.5 in CGM.
Yeah, so we
how
get,
close to that?
maximum, we get about 10 to the 12. If you put it in magnetic fields, it becomes 10 to the 11. So it's not looking great.
Because we had the same problem in the Milky Way halo when people waved their hands and said, well, you might just get 10 clumps along your line of sight, but if it's 100 or more, it's getting harder.
So for cos halos, it's 100 or more. For the Milky Way, it's like 10 to 20.
I mean, if you believe the cloudlets, then it's like 1,000. So,
Why not? I didn't see why not.
Well, because of the kinematics, actually. Like, if you're intersecting 100, different things, why would you expect the, confined kinematics in that kind of component structure?
The thing is, you can't have your pie and eat it, right? So if you think that there's going to be a lot of shear, then your cloud is going to KH away. Then you want to entrain it, but if you entrain it, then you're done.
Then you can't have a lot of
yeah.
So just to say, we did some very similar simulations and we essentially get the same results. So following the carefully
First one.
the first one, so the cloud in the making a slightly different resolution and we get essentially the same cloud flow.
That's awesome. I have to confess, we were nervous.
So one question to us is, we actually saw that there was a limit to the temperature of the objects. So in our simulations, we can only get it working up to about 10 million degrees. So did we know that right?
We did 1 million and we did 10 million. But for the application we're interested in, that's about it. But that's so we want to also. So the other thing that we're going to do is we're going to look at which I've talked to you about is jets. Maybe have supersonic flow, what happens.
Last question. What is your numerical diffusibility compared to the physical diffusibility in the region before
Well, I mean, so we don't put in any viscous term at all. So it's purely numerical, and all we do is we did a bunch of resolution tests.
So you don't know whether it is physical diffusion in this area. So it's all the numerical effects.
So the physical diffusivity could, is uncertain.